Whereas in the previous section we looked at weighting in relationship to stratification, or in other words, how certain choices for stratification led naturally to the use of weights, we can do something similar, almost a mirror image coming from multi-state sampling. For example, in multi-state sampling and clustering, subunits may be selected with differential probabilities, like the household members in the Belgian health interview survey. The reference person and the partner are selected. If there is a partner, also the partner, otherwise only the reference person. So suppose they're both present, but then there are 10 other household members, 2 out of 10 will be chosen. The reference person and the partner have selection probability 1 within the household. The other 2 have selection probability 1/5. Now that needs to be reflected in the analysis, of course. Entire clusters may be selected with variable probabilities, towns in the Belgian health interview survey, but we know somehow that while towns are very different in size, and then each time we take 50 people per town, which means the selection probability per town is very different, we also play with the selection probability of the town themselves. And these two compensate each other, so that's so-called self-weighting. Okay, good. So, let me consider another example. We have a household situation, but the households are of only 2 types, very simple. 1,000 two-person households with married couples. 1,000 one-person households of singles. So, 50% of the household consists of married couples. 67% almost of the people are married. And that's a different thing. Why? Well, if you look at households, there are 2,000 households, half of them married couples, the other half singles. That's a fact. The other thing is there are 3,000 people, because the married couples make up 2,000 people altogether. So 2 out of 3 people are married. Now, if you select a sample of 100 households and then 1 person per household, you will get 50 married persons and 50 unmarried persons. So it looks like 50% of the people is married. So a naive estimate, are you married, and a naive, not a naive question, of course, but a naive estimate on are you married is 50%. You weight the answer by the relative selection probability. Then you say, oh, the 50 people selected from the married couples, you select 1 out of 2 of the partners. So 1 out of 2, you invert 2. But in the other case, the unmarried people, not that it matters here because you have a 0, but it's 1 divided by 1. If you sum the weights, you would get 150 times 2 divided by 50 times 2 plus 50 times 1 is 150, 67% as it should be. Weighting recomposes the proper composition of the population and therefore the correct answer. If you say, what is the proportion of married households? You select households married of unmarried with the same selection probability, so that's a simple average. Message. The weights can be different in the same data set, same analysis stream, but if you're looking at different levels of the multi-state sampling. At household levels and at individual levels, the weights applied can be different. That's the message. Take the artificial population. So 3 ways of clustering, 1, 3, 2, 4, 1, 2, 3, 4, 1, 4, 2, 3. We have done that before. But we add another one, again with clusters of unequal size, cluster with unit 1 and the cluster with all 3, the other units. Okay, now the sampling units for the original one, the sampling mechanisms is simple random sampling. They all have probability 1/6. But in my case now, or in the previous case for clustering, I could only select 1 cluster, of course, if you need 2 people. So it's going to be either 1, 3 or 2, 4. So each has probability 50%. And the same for the other methods. And now I invite you to add a 4th column with the mechanism that corresponds to this guy here. And that won't be possible because the samples you would select would be of unequal size, one versus the other. And we never had that before. So what we have with the original methods is no matter what we do get one of those 6 samples. So I have said so far, almost always, can you consider a sampling mechanism as taking all possible samples of a given size, and then the sample mechanism basically identifies which one you can take and which one not. Simple random sampling, you can take all. For the others, it's each time 2 out of 3, and the corresponding selection probability. I could do one more thing here in P1 and say the second sample actually that you can take, so 1, 3, you give selection probability 1/3, the other one you give selection probability 2/3. You could do that. But it's still a subset of the same 6 samples of size 2. What's the matter now in this case? Well, here, if I take one cluster, it's either going to be a cluster of size 1 or it's going to be a cluster of size 3. So it's no longer a subselection of all the samples of a given size. No, not of a given size. The size itself varies, and all I can say is I now select from all possible samples full stop without replacement. So that's all those of size 1, size 2, size 3, size 4. That sounds grand, but actually I can take only 2 samples, so it's actually 1 of size 1 and 1 of size 3. But you get the message is by having clusters here of unequal size and not subsampling, I'm likely confronted with a sampling mechanism where the samples that I take, one take versus the other take versus the next one versus yet the next one, every time I can get a different sample size. The sample size is not guaranteed to be 2. In fact, it's impossible to be 2 in this case. So, of course, I can start to play with it and say if there would be more options, yeah, I take samples, but of at most size 2. Occasionally, I may have one that's too small, but I'm not going to have one that is too large. So that would mean if I would do that, that if I select 2, 3, 4, it's sub-selected to either 2, 3 or 2, 4 or 3, 4. That would be a different matter. Anyway, if I consider selection, if I actually choose selection probabilities 1/4, 3/4, so kind of related to if I notice that I actually have them of different size and I give them a selection probability proportional to size, well, in that case, look at my average. I get 1/4 multiplied by 4, and 4 is the estimate of the total based on the sample consisting only of 1. What is an estimate for the total based on 2, 3, 4? Well, the sum is 9, but it's only 3 units. I should actually go to 4 units, divided by 3, multiplied by 4. It's 12. So, if I then take the weights into account, 1/4 and 3/4 respectively, I do get the correct estimate. So what I take into account is the different size here is taken into account. My quantity is inflated by a factor 4 or by a factor 4/3. They're deflated again by using the weights. I inflate by a factor 4, I deflate by a factor 1/4. I inflate by a factor 4.3, I deflate by a factor 3/4, and I get 10 again. Okay, the variances for the various clustering methods, 4, 16, and then the weird one that produced 0. Now it's equal to 12, which is increased. Yeah, the units, the samples I can take are of unequal size. That is making something variable that usually isn't variable, and then the weights are different. So yes, it's not a surprise that the variance increases. Okay, good. Now, let's consider 2 more clusterings to survey town now. The one based on X, the number of building lots, and the one based on the number of newspapers delivered. So that would produce 1, 2, 3, 4, 5, 6, 7, 8 in the first case, and then the somewhat more variable one in the second case. Okay. So we now take the samples of size 2, and then that's an entire cluster that I take. But, so here is, again, the list of the potential clusters that I can take, or the potential samples that I take. In this case, remember it splits over 2 pages. There are 28 possible samples, so simple random sampling assigns selection probability 1/28 to each one of them. Systematic sampling reduced it to only 4, all probability 1/4. Clustering reduced it to only 4, all probability 1/4. And you see that no weighting is needed. You get a correct estimate all the time. The expectation is 36, except that in one clustering case the variance is huge. The variance is huge because that is a very poor clustering here. And why is that a poor clustering? Because newspapers are connected newspapers are not connected to the outcome variable very much. X is strongly connected, yeah, but that makes the samples very homogeneous. For some cases, that's a good thing. If you want to predict y from x, perfect. But if you want to use x to create a good amount of heterogeneity in the sample, so that large unit, medium-sized units, small units, they all occur, forget it. You're doing exactly the opposite, and you're blowing up your variance like hell. It becomes 320. Okay. The clusterings did provide unbiased estimators, as I said, with huge variances. So all of this is a repeat of what we have done before. Now, the relative methods of these techniques, the relative positions. Simple random sampling without is our gold standard, with a base negative correlation. And why is that a negative correlation? Well, the one with 0 correlation is simple random sampling with correlation. You take really no measures whatsoever. You don't do anything. That's actually the most vanilla mechanism. You take a ball, you put it back. The next one that comes out can still be anything. There is a bit of heterogeneity. So there is a bit of negative correlation if you sample without correlation. Why? If I sample number 4, next time it's not going to be number 4. It's going to be different from number 4, and different means negative. So that's why simple random sampling with stratification is kind of the 0 line, but yet the baseline to which we compare is simple random sampling without replacement, because if we are not going to take any design measures, that's usually the one that we take. The ones that sitting above have a negative to very negative correlation, so they are more precise. The ones sitting at the bottom are the ones with increased correlation. Okay, with clustering, you typically increase variability, especially in practice, where clusters are more homogeneous than units between clusters. In artificial examples like here, it's possible to cook up situations where it's the reverse. So, if you have clusters of variable size, and homogeneous in the survey variables, then you may have the reverse action. So variable size, homogeneous in the survey variable means decreased precision, increased variance. Okay. Now, just imagine that we are going to split our, so we have survey town. Remember that the smaller numbers means less building blocks. So the smaller numbered blocks also are smaller in size. And to compensate for that, you say, well, if you take one of the smallest, take them all. 1, 2, 3, these 3 blocks go together. But block 7 and block 8, the largest one, we do the reverse. We split them into half. They're not going to be surveyed all together. They're going to be surveyed partially. So that would mean, for example, that you designate the first cluster to be blocks 1, 2, 3, where the number of units then is equal to 6. And it becomes one of the middle group, and there's no small group anymore. Block 7, with 7 lots, or 7 buildings rather, You split that into 3 versus 4 buildings, and with 8, where you have 8 buildings, one half and the other half makes clusters 8A and 8B. So you group small blocks and you dissect large blocks. Now we take all the samples of size 1 of those. So the possible sample takes are 48, 33, etc. The expectation is still 36, still unbiased. The splitting up does not have an effect. But the variance now is 64. The corresponding variable for simple random sampling with n is equal to 1 was 336. So we have kind of not a self-weighting, but we have a correction for the fact that blocks are a very variable size. By grouping them a little bit, you alleviate that result considerably. Now we take samples of size 2. They're not listed, all of them. A few are listed, but you see the list of the estimates. Some are smaller, some are larger, but the extremes don't seem to occur all that much. So again, the average is 36. The variance has become 27 and a little rather than 124. The within sample correlation in this case is now minus 0.8. That's a very negative number, so that is very good news indeed. So placing those guys of split up clusters in the table puts the last clustering that we have seen with correlation minus 0.84 completely at the top. So that's, of all the mechanisms we have considered, by far the best, of course. Whereas simple random sampling would produce a base correlation of minus 0.14. In this case, we go all the way to minus 0.84 with the last one we have considered. So homogenizing the clusters, taking the natural clusters, but grouping some small ones and splitting some large ones can have a very beneficial effect on precision. Okay. That brings me to the end of section 18.8. It has given us a little bit of an overview of what weighting does in the context of multi-state sampling and how I can play around with clusters, cluster sizes, etc. to increase precision rather than only homogenizing the field work.